Wow, thank you. All right, I do have 200 slides, and I'm going to try to get through them all. So first I want to just give a quick shout out to this group that is the African Robotics Network is going to have an organizational meeting for presentations on Thursday from 10 to 2. And I wanted to have some thanks. I want to thank the organizers of ICRA for allowing me to come here. It's a wonderful honor. I also want to thank my three most important mentors in this field who really got me started. And I want to thank my students. These are the students that many of them are back in the lab working right now, and many of them are also here. And of course, the sponsors that have made all this work possible over the years. So I've changed the title a little bit, and I'm gonna make this about a tale of two cultures. Basically, and I'm gonna talk about agentic coding. So let me jump in. I was a kid about 7, 8 years old. I used to watch The Jetsons. Some of you may remember. It was a great show. They had a robot on there, and she would do all the chores and then play with the kids. And I thought that was great. I always wanted a robot like this. When I was a kid, my dad and I actually built a robot. It was for his chromium plating company, and it was a robot hoist. It never really worked, but we had a lot of fun making it, and it got me started in this business. And I also, as Aud said, was interested in both science and art as a kid, and I was interested in this. As I grew older, I saw this essential gap between these two things, these two cultures, as C.P. Snow characterized it, between the scientists and the artists, who really saw things differently in this world. Well, I went to Carnegie Mellon, and I really focused in on science and worked on this problem of manipulation, a planar version of part feeding. I was able to prove this result that I still remember the moment when things fell into place and the feeling of really like some cosmic force out there that made it possible. And also, at night, used to make art with robots in the lab. And my advisor, Matt Mason, when he found out, because I spilled some paint on the floor, and I had confessed to him that I was doing this, and he said, "All right, it's okay, just keep doing it." And he was very supportive. So that was really fun. I continued doing it. We made this project called the Telegarden. A few years later, at the early days of the internet, we put a robot online and let people come in and tend a garden through the robot. And most recently, I did a project with Katie Kwan, who graduated from Stanford with her PhD in robotics, but also is a professional dancer. And we did a dance performance together. She did the dancing, not me, but with a robot arm. So I've always tried to bridge those two cultures between science and art. But as Aud said, there's another two cultures that I grew to study and struggle with in a way between robotics and automation. And Aud said it well. The difference is that one robot on the moon is robotics, and 10 robots on the moon is automation, as Rajat Tila said. And I was involved in the development of the transactions on automation science and engineering, which is a complement to the transactions on robotics, and now they're both thriving, fortunately. And we're having something new called the César. This was Seth Hutchinson named this organization that is our committee to explore synergies between automation and robotics, and that's ongoing, and we're meeting on Thursday. Okay, so two cultures. Well, what I really want to talk about today is a different set of two cultures. And this is the two cultures that I see within our community here at ICRA. And it's between the model-based and the model-free. And the model-based, I call this actually begins with Newton in 1600s. And this is all the things that we studied for a long time in college, and we still teach it. And this is the essential basis of the handbook of robotics. And also, by the way, things like the workshop on algorithmic foundations of robotics and many other venues and publications. But in 2012, the connectionist approach took a major leap forward, as everyone knows, with what's sometimes called model-free methods. And deep learning was the first, and then the transformer model, and then diffusion networks. And so in 2021, the first people started talking about the humanoids again. And you may remember this, the first humanoid was announced. It was a big event. It didn't really fool anyone, but
the Tesla bot will be real. The Tesla bot will be real.
Okay, this is
the
2021.
Tesla bot will be real.
All right.
The Tesla bot will be real.
So that was a big, that got a lot of people's attention. And in 2022, of course, there was the ChatGPT moment. We all woke up one morning, and you could essentially, you realized that the Turing test had been solved or had been passed. So there were some big developments, and 2023 is quickly followed by the VLA model, where the same model is extended to actions. And for robots, where this end-to-end cameras and sensors come in, the big network is in the middle, and then actions are sent to the joints of the robot on the other side. So this really has created, I would say, these two cultures. And many people are excited about this one on the right, the model-free VLA culture. And I know if I took a poll here, we'd have a very large number in the crowd who are excited about it, and so are we. So am I. So I'm going to try and delve into this a little deeper in the course of the time we have. So I'll start with the robot data gap, which is, let's acknowledge that this is really taking on momentum since 2025. Jensen Huang was on stage with all the humanoids. He doubled down on this year, where he put on not only humanoids, but all kinds of machines, and called this the physical intelligence, physical AI, and said that this is going to be worth $50 trillion. That's like basically half the labor cost on the global labor cost. So it's got a lot of investors' attention. And everyone's wondering, so when is going to be the ChatGPT moment for robotics? In other words, when is everything going to just start working? And what you hear is people say, well, look, large data solved vision, large data solved language, so therefore, large data will solve robotics. And I want to say, I agree with this. But the question I want to ask is when? When is that going to happen? I know it will happen, but I don't know when it's going to happen. And the problem is that vision is essentially a two-dimensional state space. Language, you might say, is a one-dimensional string of tokens. But robotics, there's a lot of different parameters, and the state space is very high. So if you especially talk about a humanoid with 22 degree of freedom hands, a pair of hands with arms, et cetera, you quickly get into 50 dimensions. And that's bad, but there's also the problem that there's no training data on the internet. So what are we going to do? How are we going to make this analogy work? So my students and I just did this, made this analysis, which actually is based on something that Michael Black did, and basically that the amount of data that we have for robotics is vanishingly small. If you compare it up against the large language models, it's minuscule. So we started calling this the robot data gap. In other words, it would take about 100,000 years to read all the data that's used to train the large language model today. And if you convert that into hours, based on the average reading speed, that we only have a few years of data for robotics so far. Now, people are saying, well, data, if you know this, I also want to argue that this idea of data is all you need I want to question that. And if we look at something like Waymo, the cars, and there's a lot of successful, Waymo's not the only one that has successful cars out there, but if you compare them to Tesla has been collecting data from many of their cars over a long period. They have about 9 billion hours or miles of data, which is a factor of about 500 to 1. I might be off on these numbers, but just roughly, Tesla has a lot more data than Waymo. But yet, Waymo is actually doing better in terms of number of disengagements. So you could argue, of course, it has to do with the LiDAR and other factors. But I want to put this out there as just questioning, is data all you need? Because my friends at Waymo, I've talked with about this, and they say, yes, it's a lot of data that we use to train our cars, but there's also, inside of this, a lot of this good old-fashioned engineering. And what that means is there's a lot of modules out there that are using things like Kalman filters and PIDs and all kinds of nice mathematical models that we talked about earlier that are used to basically integrate all of these components. So good old-fashioned engineering is essentially modular. It means that you have pieces, that can be put together. They have clear interfaces, and then they're composable, but they can be analyzed piece by piece. And that also means algorithms and metrics, and I'm putting that all under this heading of good old-fashioned engineering, or GOFI. And then contrasting that with this new thing, the VLA, which is an end-to-end model. So these are the two cultures I'm talking about. The model-based GOFI, where you know who you are, that many of us are part of, and then the model-free VLA. Many of us are part of that as well. So now I want to say, as I would mention, I'm somewhat on both camps. I was a co-author on this paper. This has, I think, 150 authors, but OpenX embodiment. And one of the things, if you look at that paper, it makes the claim to generality because it has been trained on 160,000 different tasks. But I question that because if you do a histogram of the tasks, what kind of tasks they are in terms of the language that's used to describe them, well, the words picking, moving, pushing come up almost a vast amount of the time. So almost all these tasks really are, they boil down to pick up object 0 and place it in object 1. Well, that's interesting because that's actually chapter 3 of Russ Tedrake's book on robotics. And that was written before VLAs existed, and it was basically giving us a lot of good old-fashioned engineering for doing that task. And the idea is you have a camera module, you find the object, you have grasp module, you have motion planning, and you can solve that task pretty solidly. So again, I really like the good old these VLAs. They're very interesting. They're very cool. But sometimes good old-fashioned engineering just gets the job done. So let's look at this again. These two cultures. And there's a friendly. I would say there's a tension. Let's just say between them. There's some dogma. Some people are dogmatic about one or the other. And I want to just go in a little deeper. So I want to tell you a little story now about our experience with Ambi Robotics. And it's basically, I've been studying the same problem for 45 years, which is basically how do we grasp things? And some say it was because I was very clumsy as a kid. That's my mom's theory. It's true. But humans are amazingly good at grasping things. And in 2012, there was a breakthrough, as everyone knows. There was a deep learning. A lot of data, compute, and new algorithms for training. And right around this time, I was teaching a class with Shankar Sastry and Rujna Baichi and three other grad students and on robot manipulation. And we were pretty much using the textbook for good old-fashioned engineering for that. But we were watching what was happening, and there was some amazing progress being made, especially in things like image labeling. And this was basically due to this vast amount of data from something called ImageNet that Fei-Fei Li had systematically collected, this huge body of labeled images. So we started thinking, could we apply that to our problem, namely grasping? So we started calling it DexNet in honor of Fei-Fei. And DexNet was also to collect a large data set, but not images with labels, but in this case, we wanted three-dimensional models with grasps, a variety of grasps on those objects. So fortunately, my PhD student, Jeff Mahler, really got excited about this. He dove in, and he started collecting these objects from all over, and brought in a number of other students, and basically they collected objects from all kinds of sources on the internet. And we scaled them, cleaned them up, put them into a common reference format, and then we started analyzing them. So a typical object might be made of a CAD model with 1,000 little triangular facets. So a parallel jaw gripper is going to grasp that object in 2 points, 2 facets. So basically that means you have 1 million different ways to grasp a typical object. So when you look at those, what we wanted to do was think about the uncertainty that's inherent in the grasping process. So you could build a graphical model where you treat all the variables as random variables, and then they have conditional distributions and relationships. And basically what you want to come down to is what's the probability that a particular grasp will succeed. So what we do is illustrated here. We take a nominal grasp, pair of facets, and then we perturb, because we never know what we're going to get in practice. We don't know where the actual contacts are going to be made. So the pose of the object, the pose of the gripper is uncertain. The shape of the object is slightly uncertain. The center of mass is uncertain. So there's all these variables, and we sample from those distributions, and then we add up. The successes are shown in green, and the failures are shown in red. And basically, we can add this up with Monte Carlo integration, and we get a number. So for the grasp on your left, we get the number of 22. 22% chance of success, we estimate, if that's performed repeatedly with those distributions. And the grasp on the right is a 92% chance of success. So hopefully that's intuitive to you, that the one on the left, it's very brittle, right? Small errors are going to cause it to fail. But on the right, it's sort of self-correcting. So that's the kind of grasp that you want, which is robust to the natural uncertainties that we're going to face in practice. Now, the other issue is sensing. So we decided to use depth sensors because depth is, we don't care about necessarily the color of the objects or the texture, but we care about the shape, the three-dimensional geometry, so the depth sensor is good for that. But depth sensors are actually quite noisy. So if you played with them, you know that the output, even though they're getting better all the time, the output is a little noisy, and especially if there's anything that's specular on the surface or transparent. So we modeled that by basically saying, well, we know the model, the three-dimensional CAD model of these objects, but what we're going to do is synthesize an image, what this would look like to our depth sensor, and add noise to it. So now we have essentially an observation, Y, that's corrupted by natural noise that's consistent with the sensor. And with that observation, we then pair that with a particular grasp and the probability of success. And that's a data point. And then we can generate these with network. We ran it on the cloud. We can compute this for many objects. We had 15,000 objects. And so then we computed this for millions of grasps. We ended up having a data set of lots of positive examples and lots of negative examples, grasp at high probability of success and with low. With that data set, we can then train a network. And again, we weren't sure this was going to work. We needed a pretty large network, about 1 million parameters, but it started to converge. And then we had a held-out set of examples, and it started to actually perform well with that. In other words, you give it a noisy image and a particular grasp, and then it tells you the probability of success. And that seemed to really generalize nicely to new examples. So then we could use it in a control loop by basically taking an image of a pile of objects, a heap, bin, and then taking a number of sample grasps, computing very rapidly with that network their probability of success using cross-entropy sampling, and then basically finding the best grasp, the grasp that has the highest probability of success. So here's that working, and this is DexNet in about 2017-18. And on the left is a suction cup, basically using the same version of the same algorithm, and on the right is the gripper, parallel jaw gripper. Now, if you watch carefully, you'll see that it fails sometimes. It doesn't always work, but it was working surprisingly well. And it was pretty much state-of-the-art at the time, and would regularly clear out the bin of these objects that were not in the training set. So we would just bring in hundreds of objects we would find around our house, in the garage, whatever we could find to test it with. And it would clear out these bins regularly. Well, we got some publicity, and then we got a call from this gentleman. Many of you might recognize that is Jeff Bezos of Amazon. And his team invited us down to demonstrate this to him. He wanted to see it for himself. Now, as all of you guys know and really appreciate, if you have a robot that works great in the lab and then you're being asked to bring it somewhere else, that's very nerve-wracking. So we had to ship it. It had never moved before. We had to ship it. We were worried a million things could go wrong, including the lighting or a million things that could happen. But somehow it started working. And we had brought 3 bins of these objects, and Jeff Bezos came in, and he started playing with it and throwing all kinds of objects in the bin, and it was working great. Until this moment when his assistant, Ty Brady, stepped forward with his shoe. He had taken his shoe off, and he said, "Could we try it with my shoe?" Now, I will tell you, my friends, of all the things we tried it with, we never tried it with a shoe. So, but we have video of this moment, so I'll just tell you, my mouth went dry, but what could we do? So here's the moment. He says, can I do it? And we're like, okay. So he drops it in, and I'm holding my breath. I mean, we don't know what's going to happen here. It's a big moment, you know, moment of truth with Jeff Bezos right there. It reaches over, and it pulls out the shoe. Okay, this was, I will tell you, you guys will appreciate it, I think, this was the best moment of my life. You get a demo with all the pressure, and it works like that was, boy, I'll never forget it. Well, the next day, we were so inspired by Jeff Bezos' reaction that we formed a company. And Jeff and then 3 other students were graduating, and we co-founded Ambi Robotics. And it's been a journey. So we've been building, basically applying this system and extending it. And in the middle of all that, the COVID pandemic hit. So, but fortunately, we were working on this problem, which is package sorting, that turned out to be something that was considered an essential business. So they gave us permission to continue researching and developing this. And so we developed a system that we called Ambi Sort. So Ambi Sort uses the essential elements of the algorithm to pick up parts out of a bin. In this case, the parts are packages. And I'll just show you a little video of this thing running. So it scans, takes depth images, and then an industrial robot arm reaches down and picks up these objects, these packages, and then scans them for their zip code, and then puts them into a smaller bins according to their destination. So this was our first video where we had this vision that we could basically market these to lots of shipping organizations around the country. And because it's a very common problem in many shipping distribution centers. And I'm happy to say we did that. We have them all across the United States. And we work with all the major shippers and they use our system. They use Ambi Sort. Now, you might say, wait, weren't you saying that data isn't all we need? And wasn't data the part of the story here? You had all these examples. Wasn't data all you needed? And I can tell you, very much, the answer is no. It was data plus good old-fashioned engineering. To make that system work, there's a lot of engineering and modules and components to it. And it's throughout. One of them in particular is the motion planning. Because the robot has a fairly large wrist and suction head, and so it has to do a lot of very delicate motion planning to reach down into the bin, especially as it reaches deeper and deeper into the bin. That motion planning, as we all know, inverse kinematics is, quote, solved. But when you have to do it really fast in really tight circumstances, it's not solved. It's a hard problem. So we started working on this. Jeff Ignowski had a bright idea of warm starting motion planning by training it with a neural network. And that works remarkably well, was able to reduce the motion planning times considerably. So we have a second company called Jacobi Robotics that was formed by a different group of PhD students that's now out there building software particularly for motion planning. Now, let me come back to the 2 cultures we're talking about, and I want to acknowledge the bitter lesson. I know that many of you are thinking, this guy's kind of old, he doesn't know about the bitter lesson. But I do know about the bitter lesson, and I appreciate the bitter lesson, and I believe in the bitter lesson, namely that computation will win in the end. I don't have my head, in the sand, okay? But just come back to this question of when. So that's the question I really want to spend the rest of the talk on. And again, just let's talk about this in the context of the size, the real magnitude, 5 orders of magnitude of the data gap that we're facing right now between getting to the level of LLMs. So there's 2 cultures again. And so now let's talk about data. Where are we going to get data? So what's the path to getting us the amount of data we need? So one idea people have been talking about for a long time is simulation. And simulation actually is great. It works really well for UAVs. You can simulate them and then actually demonstrate them. You can take them into real, and the sim-to-real gap is fairly small, and they perform really well, and you can beat the world champion of humans at competitive racing of drones. It also works really well for locomotion. And so there's lots of systems like this for dogs and now humanoids, and you can train them in simulation to walk over all kinds of terrain, and then that seems to transfer amazingly well into real. That gap is fairly small for locomotion and whole body control. So we're seeing amazing results there. But for manipulation, there seems to be a problem. It doesn't really, the gap is very large. And it's due to a lot of components, largely because the forces are constantly changing. There's different multi-point contacts. There's deformations that seem to be very important, especially for when any real contact, especially with humans. They use a lot of deformations to achieve manipulation. Then there's the problem of instabilities of manipulation in the presence of all these fine collisions. So you get results like this where things jump around. They don't do what you would expect when you try to simulate manipulation. So this is very hard. The other thing people are doing is world models, and we've heard a lot about those in the last few months, the last year, and very exciting. You have things like Cosmos, which are basically trained on lots and lots of videos, and there's plenty of video material out there, lots of data for video. But here's an example with Grok, where we ask it to just demonstrate some examples of grasping, and you get something like this, where it's invented a third finger of something. I don't know. It's just, this is not uncommon. You get these kind of hallucinations with world models that are problematic because it's good at making things look good, but it sort of also doesn't understand, in many cases, the physics. Now, I know many of you are working on that, and so we may get that soon, but I'm just pointing out that it's not there yet. The other one is human teleoperation, and many of us are working on that. So having humans teleoperate the robot, then we get high-quality data because we're actually operating from the robot itself. And there's a lot of people out there doing this. This is now turned into a huge business, and let's just put it this way: I don't think it's an enviable job to be, doing this all day long. I know my students don't like it, and it's challenging how we're going to collect, so much data. So there's another way, which is less discussed, but I think it's important to talk about, which is production, real production. Now, that is getting robots that are out there and actually working, and then collecting data from them. So let me come back to Ambi. We have sorted, last year we hit the milestone of 100 million packages have been sorted by our systems. And one nice thing is that we have, for maintenance, have collected data on all of these systems. So we have a dashboard where we watch every single system, how it's performing. And we use that to do predictive maintenance. We could call them when there's something goes wrong, like a suction cup gets blocked or something. But it gives us a lot of interesting information, but we also save all of that. So we have records of every single pick operation that's happened, all those 100 million attempts. Now, both successes and failures. And one thing we didn't have a lot of data for, it's actually tricky to model, is bags. So right now, we have 22 years of data that we've collected over the past 4 years. Again, it's many robots working around the clock, different shifts, but it adds up to 22 years of data. And so since we're still a small company, we don't have the budget to process all of it, but we took a small amount of it just as a trial, and we developed a generative model for this, and then we tested it on real packages like this. Now, these are different than the packages we use to train DexNet because these are bags. And bags have very different properties, highly deformable, and a lot of wrinkles. So it's fairly different. If you learn models to be able to pick up rigid objects, they don't always work well in this context. But fortunately, the real data that we collected works extremely well and works much better than the data that we started with. So we call this, and many people are calling this a flywheel, namely, get something out there, get it working, then collect more data, and then you basically improve the performance of your system, your product, you can hopefully sell more of it, and then collect more data, and so on. In fact, I was presenting this, I was talking about this with Leslie Cabling and Pulkit Agarwal, and they pointed out, well, it's not really a flywheel, because you're talking about something actually not just stabilizing, but you want it to keep growing, so really it's more of an avalanche. So now I'm calling it the data avalanche. So I think that's an interesting path to getting us the data that we need. Now, there's a new part of this that I want to talk about I've only been thinking about this for the last 6 months. So let me start by going back to the question of generalist robotics, which everybody's excited about, Jensen Huang and Elon Musk and all the others. And there's companies that are really pushing this. Some of them might be here, right? So Generalist, right? The idea is we can build a model that will work in all cases. And this is very exciting for investors. So But there's this blog post came out just a month ago by York Yang, co-founder of Dyna. And he made it's a very interesting post. I encourage you to read it. It was on X. But basically, he points out the numbers that Generalist Robotics have raised billions of dollars. There's 140 different companies. And the valuations are very, very large. But if you look down in the lower right, it's a little hard to see. It's, what is it? Total useful work performed, a rounding error. Okay, he was basically pointing out that the amount of work that's actually getting paid for, productive work, is vanishingly small at this point. So what's going on? Well, I think there's another issue here which I want to bring up. This is coupled with the two cultures, because there's this idea of specialist versus generalist. That if you really want the full generalist, which is really the dream, you want to be able to start essentially a top-down approach, whereas the specialist approach, which is what robotics has done for the last 50 years, is much more a specialist. Solve one thing at a time, and then hopefully build upward toward generality. Now remember, we were talking about getting robot data from real production. So this is interesting because it sort of suggests that real production is generally closer to specialist than generalist. But there's a lot of interesting cases that are kind of in the middle in some way. So when you look at robots in production, this is some footage of an idea of a robot humanoid doing something useful in a factory. And now this reminds me of this robotics and automation distinction, the two cultures of robotics and automation here within the IEEE Robotics and Automation Society. So what we're talking about here is not fixed automation. Right? We're not talking about the thing where you just repeat doing the same thing over and over again, which you might do in spot welding or spray painting or simple electronic assembly. But we're talking about something I want to call variational automation. And by that I mean that you're doing the same job over again, but it's varied. The initial conditions are varying to a certain degree. So variational automation, I think that characterizes what we're seeing a lot. That's becoming a trend now among the companies, young starting companies like Physical Intelligence. When they show something like this, making coffee, well, that's variational automation, I would call it. You're making coffee all day long, but there's slight differences in the position of the objects and the orders maybe, but pretty much there's a structure, there's a similarity to it. Another example, you've all seen this. This is examples of what companies are starting to put out now, saying, hey, we can do useful work. We can do work with a return on investment, like this, sorting packages, right? But again, it's sort of doing one thing over and over and over again. So I've been thinking about this in the context of the Libero benchmarks that have been put out for VLAs, and modifying them a little bit to say, let's think about this as the one of just pick up these objects and put it into the basket. Let's think of that as fulfilling grocery orders. Let's say if you're like Amazon or a large grocery store, you'd be orders coming in and you want to pick out specific items and put them into the basket. Now, this can be done with good old-fashioned engineering. And good old-fashioned engineering has been around for a long time, as we said. And let's just look at this table here. You have humans actually painstakingly coding each one of those systems. It's not very general at all. Each one has to be done independently. That's why you have systems integrators out there, many of whom, a lot of us have experience with this. It's available now, right? This is how you do it. If you want to have a system, you want to automate. It's interpretable because you get code that was written by the system integrators, and it's reliable. It's really reliable. This is how basically work is getting done today in automation. And we contrast that with VLA. This is generative AI, and the hope is this is very general, right? This should work the same way large language models. You should be able to ask it anything. And it's not available yet. Not interpretable. Right? We're not going to know how to interpret these systems. And the question is, are they reliable enough to work and get us to the point where we can collect more data? Well, this really gets to the heart of these two cultures. And I just want to, I'm trying to be constructive here because I'm trying to bring us together. You'll see what I'm saying, where I'm going with this. Basically, the Libero Pro benchmark, which came out in the fall, basically tried to push this a little bit and basically said, well, if we increase the variation, let's say the VLA was tested on this benchmark and it got 100% success But if you moved the can just a little bit, a few centimeters, the success rate dropped dramatically to something like 17%. This is repeated for many different initial conditions. But if you increase the variation, you got very quickly, the VLAs tended to taper off. Now, this was also the point of this paper will appear soon from a group at Stanford, DeepMind, and Princeton, basically showing of this plot here that when that these models are not that general, that they fail when their conditions are varied more than just trivially. So how are we going to get there? This is where I think we're at an interesting point when the two cultures might just need to talk to each other in a new way. So is there another way? Is there a way to put them together? And this is what I've been trying to think about, because in coming back to the point of the two cultures, I've always trying to figure out how can we bring these together, right? Rather than create these dichotomies. So now let me talk about agentic coding. Now, code as policy was another approach that was proposed as early as 2023. And the idea here is to use an agent, an LLM, a coding agent, to write code for robotic tasks. And so there was a number of efforts to this, and this is ongoing. We're not the only one doing it. And what's interesting is, what this suggests is, well, another paradigm, if you will, that kind of combines these in a certain way. It's generative AI, but uses the pre-trained large language model, so no more data needs to be collected. It's available now. It's interpretable because you get code out that you can then inspect and analyze. And then the question is that reliable? So we've been looking at this, and in a paper that will be in ICML this summer, it's called CapX. And we developed a number of tools to basically study and benchmark this question. And there's a gem that uses a number of the standard benchmarks that are out there that you can set up to test this. We set up an initial agent system that uses a single agent to write code for tasks, where essentially you give it the task description in English, and then it just writes the code and then executes it. And we have some results. It's not working great. This is not to scale, but the system was getting about 32% success rates on a variety of tasks, way below the human baseline for coding these tasks. But we also started experimenting with reinforcement learning here, where we could have the system get better after it observes failure modes and then tries to correct them on its own. Now, this was able to get up to, in this case, the specific benchmark was able to get about 32% success. So significantly better than the VLA with this variation that was evaluated. Now, let me talk to you about something that's really fresh. Okay, this is just hot out of the oven, and this is building on the huge expansion of multi-agent coding that's taken off essentially since December. And this has been, I think, I would have to say, I'm guessing everybody in the room has heard of this or is already using it or is excited about it. This is what we're talking about, Claude Cowork, and NVIDIA just announced NemoClaw. This is really taking off. It's huge. Now, one of the challenges with multi-agent systems is that they struggle when you're trying to manage a large code base, when large code complexity, and that's what you have in these robotic systems, even variational automation. So we were trying to build this, and we looked at the CapX system, and we took a step back, and we said, well, let's think about this. And one of my students, Eric Chen, said, well, let me try and translate some of this into Rust, because Rust might help me be able to compile some of this better. And so what he found was that the graphical structure of Rust was actually quite beneficial. And then we started thinking, well, wait a second, isn't the graphical structure is actually something that's very common in robotics? Rather than just writing code, you actually generate a graph. So as everybody in this room knows, that's a computation graph in ROS. So those are very well-established models. Also, and there's all these nice components that we can inherit if we have a graph structure, which is very commonly used, things like OpenCV, which have been around for 25 plus years. And then there's there's these a system like this, which is TipTop came out just again 2 months ago. Combination of Leslie Cabling, Tomas Lozano Perez, and Dinesh Jaramayan, who basically looked at using a task and motion planning approach to generating systems that could manipulate objects. Now, their results use basically task and motion planning, which is also a graphical structure. It has a lot of nice components to it, and there were some challenges in the way they implemented, but it was definitely a step in a very similar direction. But we started thinking about what we're now calling graph as policy. So rather than code as policy, we're now generating graphs and not raw code. And so the idea is we're going to automatically generate with an agent a computation graph. And that graph structure has a number of benefits because we can decompose it into nice clean modules or nodes. And each node has certain functionality, and then that opens the door to multi-agent coding because you can have each agent looking after each individual node, and also making sure that the nodes are compatible, that their inputs and outputs are clean, and they obey certain structural constraints that make this thing start to compile and assemble and work consistently. So you can have a subgraph of these nodes. It might call the perception subgraph, another set of nodes for motion planning, and then another set of nodes for grasping. Not just with one method of grasping, but with different methods of grasping. And so the problem definition for the graph as policy is we're calling it we're going to say that we have variational automation tasks. And this is a tuple that has a language description of what you want to get done, but also you get information that you can actually, what the environment is going to be. Because whether you're in a coffee shop or a logistics warehouse, you know what the environment is. So you can take that as input. That's very valuable. You know the geometry, you know the coordinate frames, you also know the robot, you know things about the sensors. So all that can go in. And then there's a set of objects. Again, you can formalize that in a variety of different ways, but you know the set of objects, the class of objects you're going to be dealing with. And then there's a state space, which is going to be when you're actually performing one of the variational automation tasks, you're going to then be working within a state space of a subset of the objects and robot states. Then there's a belief space, which is all the possible states that you can encounter. And again, you can characterize that, maybe with a distribution. And finally, there's a reward function. It characterizes basically how well that system is going to work, basically what you want it to accomplish. And the output then is going to be a graph with a number of vertices or nodes and edges. And that's going to be used to instantiate a policy that's going to take the task and look at different for each state, generate appropriate actions. So here is what it looks like in an architectural diagram. Basically, this thing is what's called a harness, meaning that the harness is a way of basically driving this wild beast that's the agent, or multiple agents. You need a way to get them to do what you want. So that's why it's called a harness. But the gap harness basically takes in the geometry, this task definition that I just showed you, and also the language description, and it generates it breaks things down into segments. Again, it does that with the power of the LLM, and then assembles that into this computation graph, initial computation graph. And then it instantiates that with parameters based on the geometry of the objects that it may see. And then basically it goes into a self-learning mode where you're iterating over these graphs. You're trying to improve the graph by executing the resulting graph and seeing how it performs, and then modifying the graph. And these agentic systems are very good at this kind of iteration. So what you then get out of that is a G star, the optimal graph, the best one you can do, the one that performs the best, and then that gets shipped out to the robot itself. And that's where you have a graph executor, just like you have with ROS computation graphs, and that can run on a very, very lightweight computational system. So you don't need the power of the GPUs or LLMs and all that at that point. And so what you're trying to do is find this graph that will maximize your performance. So we've been looking at this, and we have 8 variational automation tasks. Several of them are built on the Libero framework, and then we've also extended some of them into real. And let me show you some of the results. So this is one that's called Make Popcorn, where basically that's just a pan, but we have a simple stove, and you have to just put the pan on the stove repeatedly, and then make popcorn. So we get very high success rate from that. With GAP, it is able to achieve 98%. This is showing you, that plot is showing you how the self-learning part of that works, so it's improving it over time until it gets sufficiently high. Here's the make popcorn task in real. So we were actually able to take our Franca robot and then actually implement the same thing. We're using Jiffy Pop there, so it can make popcorn. We've also been working with Bosch on a problem that they gave us, which is, this is something they like to automate, which is washing these crates. Right now they have humans doing it. So we modeled this, and again, with variational automation, there's variation in the position and orientation of each crate. But so far, working with the Bosch team, we were able to the GAP system is getting up to about 95% success rate. So they compared it, by the way, to human hand engineering. So a human tried to solve the same task, and humans are very good, so they got about 99% success rates. But GAP was comparable. And so we're very excited by this. 5 minutes, yeah. And then the data, we tried this problem, which is related to managing in a data center, plugging cables in and out. This is also a challenging problem. We used GAP to get 100% success rate on this task with pulling these cables in and out. And we're not only using the force sensor that's built in on the UR5 for this. But the benchmark task, let me come back to that, fulfilling these grocery orders. Well, here's how Pi 0.5 did. It was about 20% success. We reran it with these larger variations, but it was able to get about 20%. But here's how GAP performs on that same benchmark. So GAP is getting at about 97% success rate. This is over a large number of trials, large amount of variations in things that are happening in that environment. We also tried it with CapX, which actually doesn't do very well for a variety of reasons. It's not completely fair comparison for reasons we can talk about later. But we also tried it with Malmo Act, which does comparable to Pi 0.5. And then we did it with TipTop, which is an open loop system. So it's, again, these are all, not quite as fair comparisons, I would say. But GAP was able to succeed vastly better. Significantly better at these benchmarks. We also did these in real, and this again performs really well. Once you have something written in this format, it's general because you're just moving the camera around, and you can do that wherever the objects happen to be. We also tried a pack order, which is another variation where you don't care what the object identities are, you just want to put all of them into the bin. This comes a little bit back to DexNet, and again, that works very reliably. But here's the thing that I'm really most excited about was this line. What we did was we combined Pi 0.5 with GAP. What are we doing there? We basically use GAP to put the camera and the gripper right over the object before we invoke Pi 0.5. So we keep it really nicely in the center of the distribution. And that works much better. So when we give it that big head start, we almost double or triple the success rate for these VLAs. So that, to me, is a really interesting idea, that we can combine them to get really high performance in the future. And, by the way, these systems can be used to generate more data. So you get this system out there, it's running, you have it in production mode, and it's generating data, and then you can train a model-free method to continue it in the future. So we don't know, I don't want to say that's the answer is yes in the lower right, but it's some signal that it might be. Anyway, so that's graph as policy. That is all I wanted to talk about today. So I just want to end with the two cultures. The model-based and the model-free, that we might be getting to the point where these are finally coming together. And that, I think, could be very, very exciting. Thank you all.
Wonderful, fantastic talk. Thank you so much, Ken. For those of you who want to ask questions, there are mic, and please line up. And Ken is going to take the question. He's going to also, I think, set up a Google Doc so that you can ask more questions. I can see we have someone in the back. Please go ahead.
Yeah, go ahead.
Hello, interesting talk. I just want to ask, have you ever considered of using, instead of VLAs, also the new upcoming JEPA architecture, if you study it or if you considered it?
Yeah, actually, it's an interesting question. We started looking at that. We were under some deadlines, so we didn't get that working yet, but we definitely want to look at that. Yeah, I think that is, I think we're just at the beginning of this. There is a huge number of open questions. So I want to say that would be a great thing to look at, and we haven't done it yet. So please go for it. I think that's what I'm excited about, is that this is really the beginning of something that I think we'll be looking at for the next couple of years.
Thanks.
Good, thank you. Other question?
We're going to alternate. We have someone here on the right-hand side.
Yeah.
Hi. How do you think about verification? So it feels like it's becoming very easy to generate lots of code. And even when you are just purely in kind of code, it's very difficult to verify that it does everything that you want it to do. So are we going to automate this as well and get agents to decide whether or not it's correct? Do we need human supervision all the time?
Well, that's a good question. Actually, I have a meeting scheduled for when I get back after this conference with a group that actually does a code verification approach. And we're going to try that, to put that in there. So you can actually check. One thing you can do is it can certainly check for certain, for compilation. It can fine tune and make sure that things compile. Then it can check the graph structure to make sure that's accurate. But you're right. One of the things it's going to do, in our case, is we have that internal simulation. So it's going to try. One of the things that gets really interesting is where it starts to pose its own challenging cases to test itself. Edge cases, if you will. But I believe that agents are able to do that, or they'll figure, or we can get there. And then what they're asking it to basically, they're basically testing it more and more rigorously to get better and better performance over time. Self-testing. Yeah. And can that be done in real? That's really interesting, and I know some people are working on that. So that's where you have the robot actually resetting and performing its own experiments. That is a lot of interesting potential. Yes, thank you. Any other questions?
On the left.
Yes.
Sure.
Yeah. I'm curious, what is your perspective on this? I mean, there is a new trend on developing mechanically intelligent structures and structures that can adapt to uncertain environmental conditions. And how do you see this falling within this paradigm of bringing the two cultures of automation and robotics together? And maybe your perspective on where does this fall within closing the data gap?
Right. Well, so one idea is that you could imagine, I know people are looking at this, and I don't know if there are papers on this here, but you could ask a VLM or an LLM to design a structure, a mechanism for a particular task. There are some initial results that seems to be showing some promise, right? Just in the same way that there's some progress in designing of proteins and other structures like that. So I think that's a wide open area. And I do, coming back to your data collection point, certainly, because the idea of this is a way to bootstrap into production, getting systems that can work enough so that a coffee shop or a warehouse or someone will buy your machine, put it to work, and then you'll collect data. And that will help your system get better and better over time. So yeah, that's where I want to go. Exactly. Thank you.
So we're going to take just one last question, and then we have to close because we have a panel. So I'm going to take the one on the right-hand side. My right, you. Yes.
Thank you very much for your great talk. What I was wondering was, I felt that the major weakness in VLAs is that they lack in physical understanding of the world. But as your graph as policy shows, does the LLM coding agent, do you think the LLM coding agents have the knowledge on the physical world, so the graphs actually have how the world works in physics?
Well, that's a very interesting question. I don't know. I mean, it's a deep question because the same could be said for LLMs, right? Do they understand the world? So philosophers are debating that. What's interesting is they seem to be very good at faking it. So let's put it this way. I think that they don't necessarily need to understand the world in the same way that we do. I think that's clear. But they do have an understanding of the environment, especially when you watch these agents code. And I think this will resonate with those in this room who have done that. It's astounding to watch how they're able to try things. There was another group who said that they had a version of this where the agent went out on the internet, it downloaded some research papers because it got stuck on the grasping part, and then basically used those papers to figure out a different approach to grasping the objects. Okay, that's kind of wild, right? That it's able to do that on its own. So, whether or not it's understanding in the same way we do, we can talk about that over a couple of drinks. But whether it's able to actually do something useful, I am more excited about this than I have been since the internet. I will tell you, it's really, really. I think this can basically bring us together and really make progress in our field. All right, we're out of time.
Awesome.
Thank you.
Awesome. Thank you so much, Ken. Thank you, everybody. And we're going to move right away to our second panel of the day. This is a panel on sustainability. So how can you design robots that can be sustainable, and how can you design also sustainable controller for the robots? I'm going to ask the panelists to please join me here on the floor.